Hello, everyone, and welcome to another episode of Echo Live. My name is Anna, and I'm coming to you from the Michigan Science Center. Today, we have an exciting program planned, which I'm calling LN2. Just a little bit of a pun for those of you who have tuned into Echo Live in the past. Today, we'll be talking about LN2, which is liquid nitrogen. So this is the second edition of liquid nitrogen here on Echo Live. If you're like me, liquid nitrogen is one of your favorite science materials, and I really just can't get enough. So I have even more liquid nitrogen experiments planned for us today. We'll be talking about our states of matter, and we'll be doing a little bit of experimentation using our liquid nitrogen for some things we haven't yet done here on Echo Live. If you haven't done so already, go ahead and introduce yourself in the chat or the comments feature. I know we have friends joining us on Facebook Live, YouTube Live, and on Zoom. I can see and all of your comments coming in on those various platforms. You can use that chat or comment feature throughout the program so that you can communicate with me. You can ask questions, make suggestions, or answer the questions that I have to ask you. So welcome everybody, and thank you so much for tuning back in. Now, if we're talking about liquid nitrogen, we should probably pause and talk a little bit about safety first, right? Liquid nitrogen is pretty dangerous because it is extremely cold. For that reason, I have some safety materials here on my desk that I'm going to go ahead and put on right now. So safety goggles going on, and I'll just leave them on for the rest of the program. And then I also have these very stylish but very important cryogenic gloves. So these are really well insulated. They're very, very thick, and they're here to protect me from the extreme cold of the liquid nitrogen. For those of you who might have tuned in to a past episode of Echo Live where we talked about liquid nitrogen, does anyone remember exactly how cold it was? We talked about this yesterday and on our first frostology episode of Echo Live, and it is extremely cold stuff. Maybe you remember it in Fahrenheit or in Celsius. We've talked about both. But go ahead and tell me in the chat if you remember just how cold is liquid nitrogen. While you think about that, seeing some great guesses starting to come in. Jim tells me 325. No units there. I see someone in Zoom tells me 321 degrees. So degrees are a unit of measure. Maybe tell me whether you meant Fahrenheit or Celsius there. Rory tells me -210. Now, these are great guesses. Lots of people remembering some of our units that we've used in the past. Liquid nitrogen in Fahrenheit, degrees Fahrenheit, is about -321 degrees. That's 321 degrees Fahrenheit below zero. So we know if we're thinking in terms of water, right, we can pull up our phase diagram here, which talks about our various states of matter as they relate to different substances. Now, we could pretend that this is nitrogen or water, either one, but we're most familiar with water. So let's have a quick review of our states of matter and what it takes in order to change them between their various states. First, we have a gas. We know to boil water, we usually will put it on the stove, make it very, very warm, and we can turn liquid water into gaseous water. When we do that, those molecules, which we see represented as these small blue dots inside this circle, those molecules will spread out and start to have more energy. So that's just by adding heat, which is a form of kinetic energy or movement. Now we can do the opposite as well. We know that in order to freeze water, it has to be about 32 degrees Fahrenheit or 0 degrees Celsius, which is actually the easier one to think about, right? So water will boil at 100 degrees Celsius, but it will freeze at 0 degrees Celsius. And those molecules in our solid, like in these ice cubes right here, are extremely packed together, really, really tightly packed together, almost no movement of those molecules at all, just a small amount of vibration or kinetic energy inside those solid molecules. Now, according to this phase diagram, right, it's not labeled. This could represent nitrogen, it could represent water, it could represent orange juice, it could represent anything. The general rule is when we look at the molecules, as we add kinetic energy or heat, they start to spread out. As we take away kinetic energy or make something colder, those molecules will start to pack together. Now, before we start any of today's liquid nitrogen experiments, I know I did promise you a follow-up from yesterday's Star Wars episode. So as promised, if we kind of fly our Anakin Skywalker starship in, R2-D2, who was frozen in carbonite using liquid nitrogen yesterday, is totally fine. I promise we've done him no harm. R2-D2 is a really, really important part of our MySci family and of the Star Wars universe. So you can see, still totally functional. R2-D2 not harmed at all in the making of yesterday's episode. So he did not meet his end on Echo Live. He'll live to go on another day, and hopefully he'll be featured in maybe 3 more Star Wars movies. You never know. I heard that a new one was actually just announced yesterday, which is pretty exciting if you're a Star Wars fan like me. So as promised, R2-D2 just here to spectate today. So we'll just place him off to the side over there. Don't worry, he's nice and safe as promised. All right, now, oops, there we go. We are going to start experimenting with some of our liquid nitrogen today. So let's go ahead and I'll put on my cryogenic gloves, and we can actually pull out some of that liquid nitrogen, which I have here inside this thermos. The thermos is just our way of storing the liquid nitrogen before we use it for our experiments here today. And we did no harm to R2-D2 yesterday, but what fun would it be if we didn't freeze things in liquid nitrogen and then smash them, right? Because if we think about what liquid nitrogen does to the objects it touches, is it starts to condense the molecules inside, making those objects or items more brittle. So the first object we have to submerge in our liquid nitrogen is this nice stretchy green rubber tube. So you can see that it's pretty pliable, can stretch it really, really far, nice and soft, but we'll just drop it down here inside our Pyrex beaker. Pyrex is really the only glass you ever want to use when you're working with liquid nitrogen because it is borosilicate glass and it's able to withstand an extreme change in temperature. Now we'll pour our liquid nitrogen, again, negative 321 degrees Fahrenheit or negative 109 degrees Celsius, down there inside our beaker. And we are starting to freeze or condense the molecules inside that rubber straw. We'll give it just a moment and really let those molecules condense, or really let them pack really, really close together. If you can hear that noise, you're actually hearing the liquid nitrogen starting to evaporate away. It is boiling down there inside the beaker, because if liquid nitrogen gets any colder than negative 321 degrees Fahrenheit, it actually will start to boil, turn right back into a gas, which makes it much more difficult to use for experiments like this. Now, let's take a look at our straw. It is no longer nice and pliable. I can even just drop it here on my tray. And it's no longer really stretchy. It's still the same color and about the same size, but those molecules, right, just by taking away the kinetic energy, we take away their ability to move past each other pretty easily. So the straw, I could pull on it as hard as I can, and I really can't get it to come out of this shape. That'll only happen once our straw starts to warm back up to room temperature. It will start to regain some of its elastic properties. So we'll go ahead and I'll set it off to the side here, but we did promise that we'd be doing some smashing. Zoe asked what happened to my tray here. As our really cold liquid nitrogen is sitting on the plastic tray, it's actually condensing the molecules inside the tray as well. Great observation. So even though that was an accidental byproduct of our reaction here, since the molecules right under the beaker is starting to contract or trying to squeeze together, it's actually pulling the molecules inside the tray with it, which is causing it to kind of bend into this funky shape. So again, as it warms back up to room temperature, once we stop putting our liquid nitrogen inside this beaker here, the tray should go back to being flat. We'll see. Otherwise, I have more trays. It'll be okay. We promised we'd do some smashing though here. So let's go ahead and pull out our next item. We'll scoot this tray over to the side just for now. And I have some ping pong balls here. Now, ping pong balls are, again, made of a plastic, not unlike the rubber straw that we were using. They're bouncy, right? And they're a little bit squishy. So if I kind of put one in my hand here, I can squish it ever so slightly. So it's got some elasticity to it, which is actually what allows the ball to bounce. So we'll go ahead and we'll put the ping pong ball. Actually, we'll put both. Like this one to be on top though, and we'll talk about why in just a moment. All right, let's go ahead and we will fill our beaker here with some of this liquid nitrogen. We want to keep the balls both inside. I'm actually just going to take my other beaker and use it to hold them down, really get them to freeze here inside the liquid nitrogen. And the same thing is happening to these ping pong balls as was happening to our rubber straw. Those molecules are becoming more rigid as they lose their kinetic energy and they lose their ability to kind of move past each other, which gives the ball its elastic properties. All right, so now that we've left them in there for almost a minute, we'll go ahead and we'll pull out one of our ping pong balls. So we'll start with just one, and we'll see what happens to that ping pong ball if we, again, try to squeeze it in my hand. So thankfully, it kind of just popped right up off the top, and let's see what happens. Oh, no. Even with just a small amount of pressure, my ping pong ball, right, we saw that it lost all of its elastic properties. With just a small amount of pressure pushing on the ball, I actually crushed it in my hand. Now, we also have something else that we can smash. And don't worry, we've got some items that we've seen on Echo Live in the past. These are the flowers that we actually dyed on Earth Day. So we actually dyed these flowers with food coloring. We've had them for a little over 2 weeks now, and so they've really had their usefulness here on our show. And so we don't need to worry about smashing these flowers. But what makes these flowers really great is they're actually full of water. We're going to let this ping pong ball keep soaking in that liquid nitrogen, just set it off to the side. So we're going to do the same thing to our flowers as we did to our ping pong ball. We'll pour a little bit down here inside our Pyrex beaker. And then we'll take one of our, oh, a whole stem of daisies. That could be fun. All right, so we've got some daisies here. We'll go ahead and we will dip them down. We'll take maybe one of them off and save that one. And we're just freezing them in liquid nitrogen. The object of our Earth Day experiment, right, was that we know that water travels up through the stems and into the petals of our flower. We use this to talk about how flowers can actually absorb air and water pollution, which is how we got them to change different colors. So we know that all the parts of these flowers are full of water, which can be really easily frozen by the liquid nitrogen, just like we did to R2-D2 yesterday on our Star Wars episode. All right, so now that it's nice and crystallized, we'll go ahead and pull our daisies out of the liquid nitrogen and then watch what happens if we touch them just ever so gently. We've smashed the petals to bits. It almost sounds like breaking glass when we do it. And we've got lots more flowers, so let's try that experiment one more time. So again, we'll take a different stem of flowers here. We'll take some of our carnations this time, ones with some maybe nice long stems on them, like these carnations here. All right, we'll go ahead and we'll submerge them there in our liquid nitrogen, really freezing that water inside. And we said that we're taking away the kinetic energy from those molecules inside the petals, whereas normally they're nice and soft and pliable, especially since these ones are older, they're especially soft. But we really take away that property once we pull them out of the liquid nitrogen. So we'll go ahead and we'll pull these ones out. And I really don't even need to use my hand for this experiment. I can actually just tap them on the table and they shatter like glass, which is not what we're really used to when we're talking about flowers. So pretty fun. Breaking things in liquid nitrogen is one of my favorite experiments to try. Now that we've let our other ping pong ball really freeze inside the liquid nitrogen, let's take a look at that experiment. So we'll scoot a new tray that's not covered in flower scraps and remnants over into the front of the screen here. We'll use my gloves so that I can grab our ping pong ball. Man, that blue tray is really bent up by the cold beaker that's sitting on top of it. All right, so we've got our ping pong balls here, or our other ping pong ball here. We'll go ahead and we'll grab it from the beaker just by pouring our liquid nitrogen through this mesh sieve. And then I'm going to set it down on the tray, and let's watch what happens to this ping pong ball, especially if I get it angled just right. Tell me in the chat, what do you notice happening to this ping pong ball? Let me angle it down even further, see if we can get it to really start to go here. Ooh, we might. Sometimes it needs just a little bit of help, but the side of this ping pong ball has a hole poked in it. And since there is air inside a ping pong ball, which started to contract as it got colder, once it starts to warm back up, the air should start to rush out the side of our ping pong ball, causing it to spin around. It's almost like an engine. It's not working very well, but what we can do is actually just drop it back inside our cup of liquid nitrogen, set that back to the side, and we'll come back to the experiment one more time at the end of our show here. So if you notice something starting to happen, you can tell us in the chat. If not, no worries, we'll try to come back to that one. Just like we always say in science, if something doesn't work, don't give up. You can always try again, just change another variable. Seems like maybe we need to let that ball freeze a little bit longer or fill with a little bit more of that liquid nitrogen there inside the beaker. Now I have one last really cool object that we get to smash using our liquid nitrogen here today, and that is pennies. But I have two different types of pennies. Both of these are US currency, but one is much older than the other. So I've got a variety of pennies here. Some of them are very, very shiny over here on this side, and those pennies are newer. But then I also have some pennies that are a bit darker in color, and these pennies are older. We used to make pennies out of copper, out of almost completely copper, but in 1982, we started making them out of zinc. Now they appear almost the same color because we still coat the outside of our pennies with a small amount of copper, but inside they're mainly made out of zinc. Now we'll go ahead and zoom down on our table here. We'll need to drop our pennies into some more of our liquid nitrogen, really causing them to freeze. Now we can make a hypothesis about what might happen to these pennies once we pull them back out of the nitrogen. We said we're going to attempt to smash them. And I'll let you know that one type of these pennies will get smashed when we go ahead and strike them with our hammer of science here. And some of them will survive. Does anyone have a guess or a hypothesis about which of the pennies is going to survive and which ones are going to get smashed? Go ahead and tell me in the chat. What do you think? All right, someone in Zoom tells me that the old ones. Do you think those ones will get smashed or those ones will survive? While we're waiting for our pennies to get nice and cold, Kayla on YouTube asked a great question. She said, why doesn't this beaker shatter? And we said that's because it's made of borosilicate glass. Borosilicate glass has a very special way of being created that's able to withstand these crazy changes in temperatures. So even though the temperature changes really quickly and really dramatically, this piece of glass is specifically designed so that it doesn't shatter when that happens. So the molecules will pretty much maintain their shape. They won't move around too much, which allows our beaker not to break. Other glass does not work necessarily like that. So only ever use borosilicate glass when we're subjecting something to extreme changes in temperature. All right, so we've caught our pennies here. We'll go ahead and spread them out. We've got some flour bits from our beaker there, but that's okay. Now we've got our dark colored, right? We said the dark colored pennies are the older pennies, which are made almost entirely out of copper. Those are over here. And let's go ahead, since we had a few guesses, for those ones might be the ones that get smashed. Let's go ahead and try to smash one of our old pennies. Not much luck. So if you've ever tried hitting a penny with a hammer, they're pretty tough. They are strong. And the copper ones really didn't get smashed there. But let's try the newer pennies. Look at that. Our newer pennies, the ones that are zinc inside, we've almost completely smashed into tiny, tiny little pieces. What that tells us, right, is that copper is much more malleable, that it must need to get much colder than zinc does in order for those molecules to become brittle or breakable, almost like glass. So our zinc pennies, we can smash with the liquid nitrogen because those molecules are much too rigid and get much more rigid more quickly than our older copper pennies. And so again, the year they changed the penny was 1982. So any penny made before 1982 is pretty malleable, pretty strong because they're made of copper, whereas anything newer than 1982 is made of zinc and is therefore much, much, much more brittle. All right, now we've done a little bit of experimentation using our states of matter, but next we have something very interesting to talk about. So we've talked about nitrogen as a gas, which is all around us. It's in the air we breathe, and we experience nitrogen all the time. We know that we can turn it into a liquid like we've been using for these experiments by making it negative 321 degrees Fahrenheit. But nitrogen is actually able to exist as a solid as well. Now, at atmospheric pressure, where we live here in Michigan, it would be really difficult to turn liquid nitrogen into a solid. We would need to drop it down to about 10 degrees Kelvin, which is far too cold. It would completely kill all life here on Earth if we existed at 10 degrees Kelvin. So we really can't do that. But what we could do is manipulate the pressure in order to cause nitrogen to turn into a solid. We can do that using our vacuum chamber. And so what we are trying to attempt to do is we are trying to find the triple point of liquid nitrogen, or the triple point of nitrogen. This is a more complicated phase diagram than we're used to looking at here on Echo Live, but it really tells us the same things as our other diagram here. Now, in this, we're talking about both pressure and temperature and how we can use them to manipulate our states of matter. Now, normally, liquid nitrogen only exists when we make it about 63 degrees Kelvin, or I'm sorry, when we make it about 77 degrees Kelvin, which is that negative 321 degrees Fahrenheit. But that's at regular atmospheric pressure, which is approximately 1 atmosphere. But you can see, according to this diagram, that we can get these states to all exist in equilibrium if we find the point where our temperature is about 63 degrees Kelvin and our atmospheric pressure is much lower, about 0.125 atmospheres, which is really, really low atmospheric pressure. And we can only really recreate that here inside our vacuum chamber, which we've used on Echo Live in the past. So let's clear some materials here. Just scoot these off to the side where we don't necessarily need them. Grab my gloves because I do need those. And we're going to pour some more of our liquid nitrogen. I'm going to get a fresh beaker that's not frosty. We're going to pour our liquid nitrogen right here inside, and then we'll remove the air from inside our vacuum chamber. That drops the atmospheric pressure inside. Now, when you think about how a vacuum chamber works, right, we know that as we pull the air out, we're pulling out those fast-moving gas molecules. And we can do that if we just turn on our vacuum chamber. And as we do that, we are removing those fast-moving, really, really high kinetic energy molecules from the vacuum chamber itself. Put this in view. This allows us to freeze liquid nitrogen at a much higher temperature. We'll need to watch carefully because this change happens extremely quickly. The triple point is highly unstable. That's the point where nitrogen exists at a solid, a liquid, and a gaseous state all at once. Now, this will happen rapidly because the nitrogen will eventually turn to a solid, but then it will rapidly turn back to a liquid and then to a solid again. It's pretty exciting when it does happen, so let's keep our eyes on the vacuum chamber here. We can see that as that boiling begins to slow down, our nitrogen will turn to a solid. can see some of it starting to form right there inside the beaker. Do you see that solid? It's floating there on the surface, just like an ice cube, but this is not made out of water. That really is that solid nitrogen starting to form. Since there are no gas molecules left inside the chamber, there's a lot less kinetic energy, which allows this substance to freeze inside, which we could not do if there was air inside, because there'd be too much kinetic energy to be absorbed by that liquid nitrogen, and so we couldn't get it to exist as a solid. So in there, we do have our solid nitrogen, which according to that phase diagram has to be at about, I want to say, let's pull it back up really quick. It's about 63 degrees Kelvin, which is really cold. It's about negative 210 degrees Celsius. Negative 210 is far too cold that I couldn't even get a reading using my laser thermometer, even if I tried. It's way, way, way too cold. It's telling me error, the temperature is too low to get a reading with our laser thermometer. This solid is highly unstable though, really, really unstable, that as soon as we let the air back in, this will immediately turn back to a gas. So we'll turn off our vacuum chamber, and then we'll reintroduce the air inside and watch how rapidly this solid turns back into a liquid. So quickly, it all just melts, turns back into our liquid nitrogen, which we see inside the container. And that's again because we let those fast moving, high energy gas molecules into the beaker. So there it is, our liquid nitrogen, which we're pretty used to. And then it's also kind of frosted up some of our glass there just by condensing or freezing the water molecules from the air around it. Now we've got one last liquid nitrogen demonstration to show off today. It is one of my favorite. It's one of the most exciting. But before we do, as always, I'd love to take any questions that you might have. So if you have questions about liquid nitrogen or the experiments that we've used it for today, we'll try to get our ping pong ball to spin one last time before we head out. But this is a great time for you to type those questions in the chat. Let me know if you're curious about anything we've tried. And then we'll try our last two experiments together. Jamie asked, how long does it take an item to freeze in the liquid nitrogen? That's a great question. And it really just depends what the object is made out of. So things like the flowers, which are very, very thin and really full of water, will freeze really quickly. But freezing, if we want to be accurate and scientific, freezing just means that a liquid turns into a solid. So the only time we're ever really freezing something is if we are taking a liquid and turning it into a solid, like we did yesterday when we froze R2-D2 in that solid water by freezing it with liquid nitrogen. And you saw that it only took a few minutes, not even a minute really, in order to completely freeze that water solid. Other things will become more brittle if you submerge them in liquid nitrogen, but the thicker the object and the more pliable the material, the longer it takes. So if you were to try to freeze something like a basketball, which is really, really thick and made of rubber, it takes a really long time to make it brittle enough that we could smash it, whereas the flowers worked very, very quickly, only a few seconds in the liquid nitrogen. Jennifer asked, how does the vacuum chamber take air out? There was a small hose that I pulled off the back, and it's connected to a really powerful pump. So the pump has an engine inside it that actually pulls the air through the tube, taking it all completely out of the chamber. So we said that that takes all the air molecules out. It works the same way that the motor in your vacuum is able to create suction at home so that you can clean your couches and your carpets. So it all works the same way, but it's powered by an engine. Steve asked, but will we do a slime video soon? And the answer is yes. So stay tuned. I'll give you, well, maybe a little more specific of an answer, but we will talk about slime this week on Echo Live. So stay tuned. Keep checking back on Echo Live. Jamie also asked, would we break if we were submerged in liquid nitrogen? Yes, but again, since we're really, really soft and are really, really wide and thick, it would take a lot of liquid nitrogen to actually freeze someone. But this stuff is so, so cold that if you were to submerge your hands in liquid nitrogen, it would start to give you frostbite really, really rapidly, which is why medical professionals can actually use it to freeze off things like warts But again, it's pretty dangerous and should only ever be used on people by doctors who have been trained to do so. All right, let's try out our ping pong ball reaction one last time here. If the ping pong ball doesn't work for me, don't worry, I've saved the best experiment for last. Most of our liquid nitrogen has sublimated. I think I waited a bit too long, and so we might not get to that one today, but we'll try to post a video on our YouTube or our Facebook page later today if I can get it to work. It's being a little bit tricky with me today. But our very last experiment is we are going to create a cloud using liquid nitrogen. I've lost my focus there. We are going to create a cloud using liquid nitrogen, but this one's going to form extremely rapidly. So I've got a big Pyrex beaker here, the biggest one we've seen on Echo Live so far. And we're just going to pour a fair amount of liquid nitrogen down into the bottom. And you know, to me, that just doesn't seem like enough. So let's get our giant thermos, which we also call a doer here on Echo Live. Doer is the guy who actually invented this technology. It's actually a vacuum sealed container that's able to keep liquid nitrogen very, very cold. So we'll go ahead, pour a good amount of our liquid nitrogen down there inside our Pyrex beaker. And again, Pyrex is really important, and we'd only use Pyrex because what we're adding next is actually boiling hot water. So I've got my boiling hot water here in my electric kettle. What we're going to do is we're going to pour the boiling water into the liquid nitrogen, which is also boiling. When these two substances meet, it's going to rapidly vaporize the liquid nitrogen, which will super cool the air around it, causing a giant cloud to form. I'm standing in what I like to call the splash zone, so you're very lucky to be watching from home where you can't get wet from this experiment, but here we go. 3, 2, 1. Now, as our cloud settles, that brings us about to the end of our show. I am covered in our cloud reaction here. But as always, we want to take this time to thank the sponsors of the Michigan Science Center. Our donors like Ford Motor Company and Denso allow us to bring these programs to you every single day or every single weekday for free at 2:30 p.m. But today is Giving Tuesday. These programs are free, and we love that you join in. But we ask that if you are able to donate to the Michigan Science Center, this allows us to continue allowing kids to learn about science, engage in science, either from home or by visiting the Michigan Science Center. If you saw this picture on My Size Facebook earlier today, they said that this person right here is actually one of our staff members, and I'll let you in on a secret. That is me. That is me on my 4th grade field trip to the Michigan Science Center. I remember having so much fun there that day that I almost missed the bus to go home, because I was just having so much fun trying out the different hands-on exhibits and seeing movies in the IMAX theater. So if you are able to, you can visit the Michigan Science Center's website. It's listed right on the bottom. You are able to make a donation to us so that we can allow even more students to enjoy the Michigan Science Center for free. We saw about 12,000 students last year completely for free and had them engage in science. So thank you everyone so much for joining. Thank you for asking such great questions. You can continue to do so in the chat, and we'll keep checking on those throughout the day. So have a great rest of your Giving Tuesday, and we hope we'll see you back here tomorrow for more Echo Live. Bye, everybody.